this is going to be a series of videos where I systematically look at uh, physical chemistry problems from the following textbook. The idea being that even though some of these have answers in the back of the book, trying to get answer to from the question is a process all in itself. So I'm going to work this out, show you how it's done. So the textbook is Physical Chemistry by Engel and Reid, 3rd edition. I'll show you the problems. These are not all the problems, but these are the problems that I'm particularly going to be assigning to my students. So there's still good enough problems to give you the general gist of this. Since this is chapter 1, this is the first video, we'll go through chapter 1 problems. Chapter 1 problems we'll be looking at are 6, 11, 12, 13, 16, 23, 27, 28, 30, and 34. Reading off problem number 6 on this one. 6. 1 liter of fully oxygenated blood can carry 0.18 liters of oxygen, measured at T of 298 and P at 1 atmosphere. Calculate the number of moles of O2 carried per liter of blood. Hemoglobin, the oxygen transport protein, blood has 4 oxygen binding sites. How many hemoglobin molecules are required to transport the oxygen in 1 liter of fully oxygenated blood? This first problem is an ideal gas problem. So our ideal gas equation for number 6 is PV equals NRT. So we're trying to determine the moles of oxygen under these conditions. So remember, we have 0.18 liters is our volume. The temperature is 298 Kelvin. Our pressure is 1 atmosphere, meaning our R must be 0.08206 atmosphere liters mole Kelvin. So solving for that, 0.18 times 1 divided by our 298, and we'll just put in our R. Solving for that, it would give us the moles of oxygen present under these conditions, which would be 0.007361 moles. Now, all that's pretty straightforward. Here's where we get into the physical chemistry, where we actually try to think about this. Well, as I said, for every mole of hemoglobin, a mole of hemoglobin can contain 4 oxygens. So we're going to take the moles of oxygen and divide it by 4. So 0.007361 moles O2. And for every one of those, we have 4 moles O2 per 1 mole hemoglobin. And then they ask the final question, what is the number of molecules of hemoglobin? So then we have to multiply by Avogadro's number, which is 6.022 10 to the 23rd molecules per mole. If we do that, we end up with our number, which is 1.11 times 10 to the 21st molecules of hemoglobin. Moving right on to problem number 11. Use the ideal gas and the van der Waals equation to calculate the pressure of 2.25 moles of hydrogen are combined to a volume of 1.65 liters at 298 Kelvin. Is the gas in the repulsive or attractive region of the molecule potential? Okay, this one, we have to work it two different ways. The ideal one is pretty straightforward. PV equals nRT, and we are solving for pressure, given that the fact we know a few key facts. We know the moles, we know the volume, we know the temperature. So let's write down what we do know. Moles, 2.25 moles. We know the volume is 1.65 liters, and we know our temperature is 298 Kelvin. And they ask for pressure in, well, let's say they ask for ideal gas. Well, they don't really say which one, but we're going to solve for pressure in bars. So R is 0.08314 bar liter mole Kelvin. Okay. So the ideal gas is straightforward. So we're going to just be 2.25 times R times our 298 divided by our 1.65. All that is straightforward, and that would give us 33.79 bars. Now, our van der Waals equation of state is a little different. Pressure equals nRT, all that's the same, over V minus NB minus A N squared over V squared. So we need to know A and B, and what you have to do is look in the back of your book. Your book has all these values, and later on we'll learn how to actually calculate them. But for right now, look in the book. A for hydrogen, it's a gas specific, it's unit specific. So for bar liters, 0.2452. That's bar liters squared per mole squared. And B is going to be at 0.0265 liters per mole. So we have to systematically do this. So we have 2.25 times 0.08314 times 298. If you do that part, that is 55. You can do this all in one step, mind you. You do it systematically so we can check our work. 55.74537. Our V minus NB, which is 1.65 minus 2.25 times our B, which is 0.0265 equals 1.590375. And when I take those two numbers divided by each other, 55.74537 divided by our 1.590375, that portion gets us to 3505171422. Okay. All that's well and good. That gets us the main part, but now we have to consider the attractive component, attractive or repulsive component, which is the minus a n squared over b squared. So setting that up, so the minus a is our, let's see, a is 0.2452 times n squared, which is 2.25, or b squared, which is 1.65. And so that gives you, this part is negative 0.45595. It keeps going, 0413. Really, should only be 3 sig figs at best. You subtract those two parts from each other. 35.05171422 minus our 0.455950413. You'd get you sum those two parts up and you will get, so 35.0517.4559. You get 34.5957 bars. Now the final question is this an attractive or repulsive version? So we need to compare our pressure ideal to our pressure real. So is this pressure higher? Is this pressure lower? Well, our pressure ideal was 33.79 bars. Our pressure real is 34.5. So we see an increase in pressure. Now, this increase in pressure is brought about by gas particles pushing each other away. So this is more repulsive. Had this been lower than the ideal, this would be in attractive mode. That is question 11. Looking at question 12. A rigid vessel of 0.400 meters cubed containing hydrogen at 21.25 Celsius and a pressure of 715 times 10 to the third pascals is connected to a second rigid vessel with 0.750 meters cubed containing argon at 30.15 degrees Celsius and a pressure of 203 times 10 to the third pascal. A valve separating the two vessels are opened and both are cooled to a temperature of 12.2. What is the final pressure of these vessels? So this one is a bit of a hassle. It is not particularly hard, but we have to treat it as a couple different problems. One, you have to remember how to convert different gas pressures. Two, you got to remember that ideal gas can be summed up together so that on Dalton solved partial pressures. So we have to do a couple different ideal gas conversions. So we have to figure some things out. So let's treat each one separately. Number 12. For one, we have a volume of 0.400 meter cubed, which is, quick conversion, in a centimeter cube, there is 1 milliliter. So in 1 meter cubed, there is 1,000 liters. Real quick. So in 1 meter cubed, there's 1,000 liters. So this is 400 liters. As I was saying, and so the first vessel contains 400 liters at a temperature of 21.25 degrees C. So we add in 273.15 and 3.15. You get 294.4 Kelvin and a pressure of 715. 715 times 10 to the third, so 7 pascals. Well, there is 10 to the fifth pascal in 1 bar. Fifth pascals, 1 bar, so 7.15 bars. Now that's V1, T1, P1. Now for V2, T2, and P2, same general process. It's 0.750 meters cubed, so that 750 liters. Temperature is 30.15 C. 5 plus 273.15. That's 303.3 Kelvin. And pressure was 203,000. So which is 2.03 bars. Okay. Now, to do this, we are first going to determine the moles of each gas individually. We're going to add them up. We need to combine to calculate our new temperature. We're going to combine the temperatures will have changed. So we'll have a new temperature, and we're calculating a new pressure. Had the two gases been added to the same container and the volumes had not changed, we could just take the moles and sum them up and then refigure it in. But because these two containers are being combined, we have to take that into according. So 400. PV equals nRT. PV or RT equals N. So 400 liters times 7.15 bars divided by 294.4 times 0.08314. Doing that real quick, 400 times 5 times 294.4 divided by, well, I'm going to scoop that up, divided by 0.08314. Doing that first calculation, you get, all sig figs considered, 117. 117 moles. Doing that again for situation 2. 750 times 2.03 divided by 303.3 times R. Okay, so 2.03 times 750. 8314 gets us 60.4 moles. And so the sum and total would, of course, be the sum of those two. 60 plus 117 would be 177 moles. Okay, that gets us part of the way there. However, we need to consider the volume total. So we're adding V total. V total would be V1 plus V2, so 750 plus 400 gets us to 1,150 liters. And as we said, the temperature would decrease to 12.2. So the T final is 12.2. Add in 273.15. So 285.35. And as we said, the moles were 177. If you want to be one, let's leave that sig fig in 177.4. Not going to change too much. Okay, so 177.4 times our R times our temperature, 285.35 divided by our 1150. 177 times 285 point, and that would give us a pressure of 3.66 bars. So it's just a systematic approach. So quick reminder. So we had to figure out the moles of each gas, the one thing we didn't have. Then we had to take into account Dalton's law of partial pressures. So when they combined, we could just simply add up the moles. But because they were combined into one larger reaction vessel, the volume changed. And so we had to take that into account. Looking at problem number 13. 13 reads, a mixture of oxygen and hydrogen is analyzed by passing it over a hot copper oxide through a drying tube. Hydrogen reduces the copper oxide through the following reaction. Copper oxide plus hydrogen goes to copper and water, liquid. And oxygen then reoxidizes the copper by copper plus 1/2 oxygen goes to copper oxide. At 25 degrees at 750 torr, we have 172 centimeter cube volume of mixture yields 77.5 centimeters cubed of dry oxygen, measuring at 25 degrees and 750 torr. So the temperature has not changed. The pressure has not changed. The only thing that's changed is really the volume, thus the moles. The passage over the copper oxide and drying agent. So what is the original composition of this mixture? This is a real puzzler. So for this guy, you have to first think about this, that we have two competing reactions. We have copper oxide plus hydrogen goes to copper and water, and copper plus 1/2 of oxygen goes to copper oxide. If we sum up these two reactions, what we get is the net reaction of hydrogen plus 1/2 oxygen goes to copper oxide. Sorry, goes to water. And water is going to be instantly removed. So what this means is in our changing of volume, we go from a volume of 172 centimeters cubed, which, as I said, centimeter cubed, there's 1 milliliter per centimeter cubed, so 172 milliliters of volume. V1 or V2 goes to 77.5 milliliters volume. Those two changes in volume involve the loss of both 1 equivalent of hydrogen and a 1/2 equivalent of oxygen. But we're losing both of them at the same time. So we're losing, what we need to figure out is how many moles of gas are lost in these two volumes. Because we're told that this 77.5 is made out of oxygen, pure oxygen. So the difference between V2 and V1 minus V2 is going to be a 3 mole gas mixture, which is a 2 hydrogen to 1 oxygen. Now, if we can figure out how much gas is lost in here, we can figure out what is the mixture of each gas. So let's find out how many moles of gas we started with and how many moles of gas we end with. And from there, we can figure out how much gas was lost, and thus how much we started with in the first place. Zp is 750 torr. Real quick conversion. There is, in 1 atmosphere, 760 torr per 1 atm. I'm always going to be converting into the most common unit, the easiest one to convert into. So 750 divided by 760 gives us 0.9868. I'm going to leave it there. It still goes on, but I'm going to leave it there. At 25 degrees plus 273.15, it's 298. Let's see, 25 degrees, yeah, 298 Kelvin. Okay. And milliliters we can turn into liters without a problem. So all this, we have everything we need to start. We just had to figure out how to first think of this problem. How to first even approach this problem, because this problem is a brain bender before you get to this point. Once you get to this point and you've thought it through what you want to do, it's pretty straightforward. So PV over RT is going to be our N. So we say pressure is 0.9868 times 0.172 divided by 298 divided by our R, which is 0.08206. So our moles in our first situation is 0.006937. That's our initial moles. Now doing this again. Same pressure, different volume, So in this case, 0.0775 298, and R, we get the moles of gas at the final part, 0.03126. So there's our moles initial, moles final, and the delta moles is going to be the difference between the two. Take that difference, would get 0.003811. Remember, this is not moles of hydrogen loss. This is moles of gas mixture, which is a 2-to-1 ratio of hydrogen to oxygen. So of this mixture, 2/3 delta N times 2/3 will give us our moles of hydrogen. Delta N times 1/3 plus our N final will give us the moles of oxygen. So doing that, we get the moles of hydrogen we have in our original starting mixture, 0.02541. We figure out the moles of oxygen in our original mixture is 0.004396. So that's moles hydrogen, moles oxygen, and what percentage is each gas. So you're going to just take this value and divide it by the total. So 0.002541 divided by our 0.006937. You get it's what? 36.7% hydrogen, and that means it's 63.3% oxygen. So this was the first problem that was actually really rather hard. Looking at problem number 16. Aerobic cells metabolize glucose in the respiratory system. Reaction proceeds according to the overall reaction of 6 oxygens, and 1 glucose molecule goes to 6 CO2s and 6 water liquids. Calculate the volume of oxygen required at standard temperature and pressure, STP, to metabolize 0.025 kilograms of glucose. STP is 273 Kelvin and 1 atmosphere. Assume oxygen behaves ideally at STP. So really are other this is the first time we're going to combine into our general chemistry knowledge, really into there, and not just ideal gas. So we need to figure out how many moles of glucose do we have, thus how many moles of oxygen do we need. So starting with, we have 0.025 kilograms of glucose. The one thing you got to get used to is converting C6H12O6. So that is 25 grams of glucose. We need to look up the molar mass. That is a process. You can look that up, and that is, there's 180 grams of glucose per every 1 mole of glucose. And based on the chemical reaction, for every 1 mole of C6H12O6, we need 6 moles of oxygen. Just because we're working through complicated stuff doesn't mean we have to forget our old stuff, old science. So 25 divided by 180, all that times 6 would have 0.025 8,333 moles of oxygen. And at that point, they asked what volume, STP. So it's just 0.8333 times R in this case, which is 8206. Because it's STP, it's 273 divided by 1 ATM. Doing that, that's 18.68 liters of oxygen. That one, all things considered, not a particularly bad problem. Not something we need to stress over overly much. Moving right along to problem number 23. 23. Assuming that air has a mean molar mass of 28.9 grams per mole and the atmosphere has a uniform temperature of 25 degrees C, calculate the barometric pressure in pascals in Santa Fe for a height of 7,000 feet. Use the information contained in problem 20. Problem 20 has a crazy equation of pi equals pi not pi 0 times the inverse natural log, the e times negative m sub I g z all over rt, or pi is the partial pressure at that height z, pi naught is the partial pressure of the component at sea level, g is the acceleration due to gravity, r is a gas constant, t is absolute temperature, m sub I is the molecular mass, and the z is the height. So with that in mind, looking back at this problem, so problem number 23, we have the molar mass is 28.9, z is 7,000 feet, and so we may have to calculate feet into meters just to get the units right. G is 9.8 meters per second squared. And let's see. R is, okay. R's we're going to have to figure out. And let's see. This is gas constant, and let's see. T is the temperature. T we know as 25 degrees, so 298. So, okay, looking at this one. We have to keep in, and we have to also find the partial pressure. Okay, so the key here is units. This equation makes almost no sense unless you have units. What we have to achieve here in this equation is P sub I equals P sub I naught epsilon molar mass GZ over RT. All the units in that E factor have to cancel out so that pressure equals pressure. So we have to have the units of R. R has to be in 8.314 joules per mole Kelvin. And the beauty here is that a joule, 1 joule is equal to a kilogram meters squared per second squared. So working that out, we have R which is joules per mole Kelvin, times T in Kelvin. Those cancel out, and we're left with joules per mole. Molar mass is going to be typically grams per mole. So replacing joules for kilogram meter per second squared, we have kilogram meters squared per mole second squared. Then on top, we have meters per second squared. Now, if height is in meters, that takes care of that. So what we need molar mass to be in is kilogram per mole. All of these cancel out, and we can get that term. Now, P sub I naught at standard temperature is going to be 1 bar. 1 bar. So we're trying to figure out what would this be at much, much, much higher. So first things first, we're going to turn molar mass into kilograms per mole. So that should divide 1,000 grams per 1 kilogram. So that becomes 0.0289 kilograms per mole. Next, we're going to turn feet into meters. Feet into meters. You can multiply by 12 inches in a foot, 2.54 centimeters in an inch, and a centimeter, yeah, and then 1/100 centimeters in a meter to get you 2133.6 meters. So doing this, your total pressure, 1 e to the factor of 0.0289 times 9.8 meters per second times 2133.6 all over 8.314 and 298. You do that, you get 78,347 pascals, or 0.783 bars. That one, among all, is P-Chem in a nutshell. A complicated ass equation with separate units, and you got to figure out how these units cancel out. Otherwise, it's just mumbo jumbo. What we're doing is we're putting this in, and so all the units cancel out. The equation isn't hard to use as long as you have everything in the right units, but you have to think of how those units fit together. How those units fit together in order to solve this. Now, this may not be exactly the same as in the back of the book. It's maybe a little fudging, like whether rounding here or rounding there, what's causing it to be slightly different, but it's pretty darn close. But that's what it all comes down to, units. You got to watch your units. They all cancel out to get that the whole E power. The whole E power is unitless because they all cancel out. And so if I have 10 to the 5th pascals down here, 10 to the 5th times E is going to be pascals. Looking at problem number 27 at this point. A mixture of hydrogen and ammonia has a volume of 139 centimeters cubed at 0 degrees C, 1 atmosphere. Mixture is cooled to a temperature of where liquid nitrogen, at which ammonia freezes out and the remaining gas is removed from the vessel. Warm the vessel at 0 degrees C and 1 atmosphere has this volume. Calculate the mole fraction of ammonia in the original mixture. So this is just like the copper mixture, but a little bit easier because we start with the initial volume. So 27, we have a volume initial of, we'll call it 139 milliliters, and temperature of 273, 15, pressure of 1 atm. We go to V final of 77.4. The T's don't change. The P's don't change. So we're finding the moles initial, moles final, and using that to figure out how much hydrogen was removed. So the mixture, PV over RT. Hopefully this is getting a little bit old hat at this point. 0.139 liters. 8206 times 73.15. So the initial mixture is 0.006201 moles. Do it again. 1 times 0.077. Let's say 774. 0.8206 times 73.15. 0.003453. And we don't even have to subtract them because we want to know what mole fraction is the nitrogen. So the mole fraction is moles nitrogen, moles ammonia over moles total. So 0.03453 divided by 0.006201, and that's going to be our unit list value of 0.557. 28. A sealed flask with the capacity of 1.22 decimeters cubed contains 4.5 grams of carbon dioxide. A flask is so weak that it will burst if the pressure exceeds 9.5 times 10 to the 5th pascals. What temperature will the gas exceed that at a bursting pressure? So 28, all things considered, is just uses some funny units. You have to do some conversions. 28, 1.22 decimeters cubed. If you look up the conversion, that actually is equal to 1.22 liters. They say the P max is 9.5 times 10 to the 5th pascals, which it also happens to be 9.5 bars. And they say moles, if we have, in this case, 4.5 grams of carbon dioxide, so we need to turn that into moles. 4.50 grams CO2, it happens to be, what, 32 plus 12, 44 grams in 1 mole. So we have a moles of 0.102273. So what is the temperature max? So T max is equal to PV over NR. 9.5 times 1.22 divided by 0.102273, and R would say, oh, I could heat this up to 1363 Kelvin. Last two at this point. Number 30. Carbon monoxide competes with oxygen for binding sites on hemoglobin. CO can be poisonous if inhaled in large quantities. The safe level of CO is 50 parts per million. When CO level increases to 800 parts per million, dizziness, nausea, and unconsciousness can occur, followed by death. So in the partial pressure of oxygen in the air, sea level is 0.2 atmospheres. What proportion of CO to O2 is fatal? So the amount of O2 isn't going to change. But we're saying 800 parts per million. We're turning parts per million into atmospheres. So we're saying oxygen is, the pressure of oxygen is 0.2 atmospheres. So parts per million. If we have 800 ppm, parts per million is like usually items over items total times 10 to the 6th. So and it's usually moles over moles total, but we can do it as pressure over pressure total. So what's the pressure of gas over the total pressure? 10 to the 6th. Well, we can assume at standard conditions we have 1 atmosphere. So what you end up having is 800 times 1 divided by 10 to the 6th would give you partial pressure. So the pressure of CO2 becomes 800 divided by 10 to the 6th, which is 0.0008 atmosphere. So at what ratio is that dangerous? 0.0008 divided by 0.2, you'd get 1 to 25, 250 oxygen. So if there's 1 molecule of CO2, one atmosphere of CO2 for every 1 atmosphere for every 250 atmosphere of oxygen, that ratio would become deadly. So that's all you really need. Ratio of 0.004. Okay. Last problem. Problem number 34. Calculate the volume of all gases evolved by the complete oxidation of 0.375 grams of amino acid alanine. The products are liquid water, nitrogen gas, carbon dioxide gas, and the total pressure is 1 atmosphere. 298. So we have 0.375 of 0.375 grams of liquid alanine. So alanine, as they give us, is, I'm going to count the number of carbons and hydrogens. They give us a CH3CHNH2COOH. So C3H4, 5, 6, H7NO2. C3H7NO2. Now, when you saying complete oxidation, so that means process with oxygen, got to balance this chemical equation. We're going to produce N2, a half mole. We're going to produce CO2, so 3 moles. And we're going to produce H2O, 7 halves. So this oxygen needs, put there, let's see. Halves, let's see. 6, think that's 5/2. Yeah. Something like that. If I'm balancing that right. Okay. With that in mind. Never mind. And please note, in here they say liquid water. So liquid water. So we're only producing gas here. The volume of all gases evolved. So we need to first calculate the moles of amino acid, then the moles of nitrogen, and finally the moles of oxygen. From there, we can figure out how much the total volume. Okay, so 0.375 grams. Alanine has a molar mass of about 89 grams per 1 mole. So moles of 0.004213 moles. So we could actually combine these together. I'm going to actually do that and save myself a little bit of trouble. So for every 1 mole of alanine, for every 1 mole of alanine, so 0.004213, because these are ideal gases, for every 1 mole, we will produce 3.5 moles of gas. So 0.004213 times 3.5 based on this balanced chemical equation here. So you'd produce 0.0147455 moles. And then we'd use our ideal gas equation. We want to know volume, so it would be R nRT over P. So lastly but not leastly, 0.0147455. We have pressure of 1 atmosphere. We have temperature of 298. So 0.06 times 298, you get 0.3606. Maybe not quite perfect as it has in the back of the book, but pretty darn close. It probably has something to do with rounding in our molecular formula. But oh well. But that is the end of chapter 1. That is all the chapter 1 problems that I have assigned in my homework. So hopefully you'll find this somewhat useful and be able to use this as you work through assignments. Thank you. Goodbye.